Okay. Sorry, I'm a few minutes late because I locked up myself in my office. I was waiting for the police to come to open my office, but they never come. So, so today we are going to. So I had a lot of students asking me questions, and especially with regard to the kind of the complexity of the homework as well. So what I wanted to do is today really I go back to chapter 8 and review two important contents. So before we doing the quiz on Wednesday, so there's no quiz today, but there will be a quiz on Wednesday. So hopefully this will help you to uh, to prepare for the quiz as well. But of course, the quiz is only a matter of checking your understanding of the class. It's not the end of the day. So let me go ahead and then open my slide. Okay. So we're gonna go through today, and it's mostly really just chapter 8 and a little bit of chapter 9. We're gonna first go through the Wilson and Widlar current sources, just explain how it works. And then we're gonna dive into the common base and common gate amplifier, which is in the book. I probably don't have time to go to this today. So hopefully we'll cover enough details about those two amplifiers. Now, one of the observations that many students come to me asking me whether we need to. Second, I think this is the police department calling. Thank you. Is it better now? Okay. So he worked for Tektronix, and he saw that the current mirror we have, the current source that we have, like we learned in chapter 8 in the beginning, does not provide enough output resistance. So he designed the circuit such that it would provide much more output resistance. You know, I explained many times, why do you need a large for amplifier? Why do you need a large input resistance and a smaller output resistance? Because of the divide function of any circuit. Okay? When you have an input, you always have internal resistance. And that input resistance of your amplifier, if it's too small, it doesn't get enough input. It has to be very big. So that's why for this circuit, it will increase the output resistance. So let's look at the circuit and initially look at how it works. So I'm going to redraw the circuit because that part is used for your reference. I'm going to redraw the circuit so that we can go through it together, so you can see how the currents are calculated in the circuit in each of the branches. So there are two BJTs. They are both N-type BJTs. Okay. So in this circuit, what you can see here, at the bottom, you have a voltage supply. And then at the top, you have reference current coming in. And you have two BJTs. You probably know what this is, right? These two in a pair, it makes a current mirror. It makes a current mirror. And adding a Q3 becomes a Wilson bipolar current mirror. Bipolar refers to BJTs, bipolar junction transistor. So it calls bipolar. So Wilson has both a bipolar and also a MOSFET current mirror. So because this base is connected to the collector, and you can see from here voltage from here to here is the same from here to here. So these two will share the same VBE. Therefore, these two will have the same current. That's why it's called a current mirror. So these two will have the same current. And then let's define a current of IC over here. And this current IC coming in. So these two transistors will have exactly the same current, IC coming in, IC coming here. But remember, the base of this BJTs will have current. With MOSFET, there's no current in the gate. But the base of BJT has current. How much current into each of these transistors? Can you tell me? How much current is into each gate? It's IC over beta, right? So it's IC over beta. And here is IC over beta as well. So this current coming this way, this current coming this way, that current has to come from here. So that's why the current over here is going to be 2 IC over beta. Okay. So, and then how much is the current over at the emitter of Q3? Can you tell me how much current is at Q3? This I here, it's called IE3. It's going to be IC plus 2 IC over beta, right? So that's the current over here. And then how much current is flowing here then? That's called IB3. How much IB3? because you know the IE is 3, so IB3 will be IE3 over beta plus 1. You got IB3. And then once you know IB3, you can calculate IO, which is IB3 plus IE3. And altogether, you will be able to get this current. It's going to be the equation up over at the top. So IC over 1 plus 2 beta over beta plus 1. That's how, if we simplify the whole thing, we'll get IO, which is current. The IO is the current over here. So that's really how you can analyze the current. And this transistor here all like matched. They're all symmetrical. Every parameter is the same. And then the way to look at it is to look at each branch. Again, starting with the IC over here and IC over here. And then this IC over beta, this IC over beta, and this is 2 IC over beta, and this is IC plus 2 IC over beta. And then you got that IB3 calculated, and then you get IO calculated. So that's how you get the final current. Now the current I reference over here, this I reference is going to be IC plus this IB3. So you can see here the I reference and IO are slightly different. They're not exactly the same. But in this case, if beta is approaching infinity, which in some cases we can do, and then you will see that this IO will be exactly same as I reference. And it's the same as IC, which is you can do the simplification. So that's how this Wilson current mirror works in a DC state. The reason, of course, is not to figure out like the little current on each branch is important, but that's really not why we need a Wilson amplifier, the Wilson current mirror. The reason we need a Wilson current mirror is because it's going to increase the resistance. So in order to calculate the resistance, we need to draw the small signal circuit. And the small signal circuit will start from, well, I mean, we can start from any transistor. Like I explained many times, when you draw a small signal equivalent circuit of this, you always draw the equivalent circuit of the device and then find out which one is connected to which terminal. So that way you can eventually finish the drawing of the whole circuit. So what we can do here, because it's already showing here, so let me do this. So let me delete, cut, and this, and I believe we do have the circuit listed here, so we can always go to there, and if we forget, we can always go to draw our circuit over there. So we can start from Q1, which usually I mean, the way that the book does it is that you always from 1, 2, and 3. So that makes your life easier. So Q1, we can draw Q1 circuit by doing this. Okay, so this is Q1, and we have this emitter. We have this collector, and we have this space. Cm times V pi 1. Cm1 times V pi 1. Okay, so now we figure out for Q1, what is connected to the emitter? Look at Q1. What is connected to emitter? It's a voltage source in AC becomes a ground, okay? So emitter is connected to ground. So let's ground it over here. And what is connected to the collector? the collector is connected to the emitter of Q3. So now, okay, so now I guess we need to draw Q3. So let's draw Q3. So Q3. Okay, so the emitter is connected to Q3, so we can connect them like this. So Q3 emitter is connected to collector of Q1. Okay. And then Q3 emitter, yeah, Q3 emitter is connected to Q1 collector. So now we got this connected. Now let's look at what happens to the base of Q1. The base of Q1 is connected to the base of Q2. So which means we need to draw the equivalent circuit of Q2. Now remember, because their bases are connected, so the draw is to draw this. To draw the circuit also flip. So this is now figure out these connect together. This is R pi 2, O2, this is RO1, R pi 1, this is R pi 3, RO3. Okay, so there is also one more connection. Look at it here. The base is also connected to the emitter or the collector of Q1. So which means we are connecting here. Do you see? We are connecting, we're connecting from here to here. So base is connected to, so base was initially here and we connected. So we're connecting this together. So we connect that. Okay. So now what is connected to the collector of Q2? The collector of Q2 is connected to the base of Q3, right? See, the collector of Q2 is connected to the base of Q3. So which means we need another line to connect from here to here. So now we finish all the connections. So pretty much it's very simple now because it's all finished. So the only thing, of course, is that we figure out which is which. Like this one, for example, is GM2 times GM2 times V pi 2, and V pi 2, V pi 1 are the same. So and then that one is GM3 times V pi 3. So what we need to mark up is from here to here is V pi 3, and here is GM times V pi 3. And here is this one is GM times V pi 1, this is GM times V pi 2. And we know that V pi 1 is same as V pi 2, which is over here. They're the same. And so there's one more thing in the book. You'll figure out that this is a current, controlled current source. But in this case, especially in current mirror, you see this very often. They convert this to a resistor. So how can we convert a current into a resistor? Well, basically, this is a controlled current source. This is not constant current source. This is controlled, which means this is controlled by what? By what? See, this is GM times V pi 1. And where is V pi 1? V pi 1 is from here to here. Well, this is the ground. So which means from here to here is V pi 1. So if I look a resistor, let me call this something resistor, but just the capital R. And I have current flowing, which is GM times V pi 1. And how much voltage would I get on this resistor? And we know that gives V pi 1. So we have V pi 1 equal to Gm times V pi 1, which is the current, times R. That gives you the voltage. So current times resistance gives you voltage. Now you have V pi 1 on both sides. It's cancelled. Then we got Gm times R equal to 1, which means R equal to 1 over Gm1. So that's why you can eventually replace this one with the resistance of 1 over Gm1. So this becomes resistance. If this becomes resistor, you see here, 1, 2, 3. And this 3 all in parallel. Not only that, how about this here? Because this is also ground. This R pi 2, all 4 resistance are in parallel. But this is not in parallel, okay? But this is, see, this is not connected. So this is separate. So all these 4 resistors in parallel. So basically, now you can really simplify the circuit to like very, I mean, from the next page, let's look at. Okay. So here we have the circuit that was wrong. We have 1, 2, 3, 4 in parallel. Then have a current source over here. And we cannot convert this one into a resistance. Why? Because we don't know how much voltage is here. This voltage is not given. So this is this times V pi 2, but from here to here is not V pi 2. So in the book, it has to do analysis to find out how much resistance will we get. If we want to find the resistance, basically the resistance is looking into here. You look at here, for example. This is where you connect your circuit. So we look at that point. So what we do is we add a voltage source, and we find how much Ix. Right? So then we use Vx minus Ix. We got like the resistor RO. So you can apply a voltage source here. When you see this circuit has how many nodes? This node over here, or this whole thing is one node. So that's even though there's a line in between, but they're actually one node. And there's one node over here. So they're basically 2 nodes. Then you can write a nodal equation to analyze it, or you can write loop equations to analyze it. But in either way, you can write equations to solve for given Vx to solve for Ix, or given Ix solve for Vx. The book gives you step by step how to solve for Ix, and eventually they use Vx over Ix to get RO, and the RO was given eventually was okay. So you see how when they did this one, there's easy way to really do the book really actually it's pretty smart, and they do it like this. If you look at the current coming here, it's Ix, but this current coming out here is Gm times Vgx. So how much current is coming here this way? Let's call it I1. So you see I1 equal to Ix minus Gm times V pi 3. And then how much voltage is from here to here? No, plus minus here. I call it V1. So V1 equal to I1 times RO1. So that's how they get that voltage. RO3, yeah, RO3. RO3. So if you have V1, and then how much voltage is here? V2 is Vx minus V1. Yeah, so V2. Okay. So and how much voltage from how much is R pi 3? Because Ix coming this way, then you got, well, not yet. So we need to I1 equal to I1 times RO3. So I1, no, actually they call this I1. Oh my God. I made it make it. Let's call it I3. So I3 equal to V2 over the fourth resistance in parallel. Yeah, I don't know, called R. Let's call it R3. So R3 basically equal to this R pi 2 in parallel with I pi 1, and in parallel with 1 over GM1, and in parallel with RO1. So this is R3 over here. So once you got this one, I3, and you have I, or they call this I2, or call this I4. So I4 equal to Ix minus I3. And then you have V pi 3 equal to minus I4 times I pi 3. And then, yeah, so now you basically can calculate here, which I call this I4. Then you can calculate this V4. So you can calculate V4 equal to, well, first of all, we need to calculate this I5. So let's calculate I5. So I5 equal to I2 minus I4 minus GM1, GM2 times V pi 2. So we got I5, and then we have V4 equal to I5 times RO2. So all the way, like every step, you just simply manipulate to figure out each one. So from Ix minus current of this one, get the current of this one. Current times this one gets voltage. This voltage minus this voltage get this voltage. This voltage divided by this resistance get the current. And that current minus this current give you this current. And this current times that voltage, the resistance get that voltage. And to get that voltage, and then this current minus this current get this current. And from this current times this get this voltage here. So basically you got this set of equations, and you can solve for the stuff, and then you can get RO. So RO eventually was equation was here. I don't know why equation is not so clear, but it's RO is 1/2 beta 3 times RO3. That's the final. That's really the final solution. That's the final solution. If we have Wilson current mirror that was built using this MOSFETs, it becomes even easier because if you look at the circuit over here, there's no current. So let's look at here. So there's no current over here. There's no current here, no current here. And the bottom is a current mirror. The bottom is current mirror, which means the current over here, if you call it ID, which is the same as the current ID over here. And since there's no current in the gate, so basically this IO equal to ID, which I reference also equal to ID. So everything eventually equal to I reference. So that's how this works. Every current is the same. So in the BGD case, if you neglect, if you think beta is infinity, it's the same thing. So every current is the same. Okay. In order to find out the resistance, we do the same thing. So we draw the small signal equivalent circuit. So here you start by drawing this one, Q1, and then you draw Q2, then you draw Q3. The good thing about it here is that the gate is no current, so it's an open circuit. So it becomes a little bit easier to do it. So maybe what we can do is this: we can remove this. See, Yeah, we have it here. So we can remove the circuit over here, and let's draw it together so that we get a better understanding. So for this one, let's start by again Q1. So Q1 has this MOSFET has a gate here, and we have this one here. Okay, so for this Q1, this is GM1 times R times VGS1. Okay, this is VGS1. So the source is grounded. That's easy, right? Source is grounded. And then we look at the gate. Where is the gate connected? The gate is actually connected to two things. One is to the gate of the Q2, but the other one is connected to the drain. So let's connect to the drain. Right? The gate is connected to the drain, so this is the gate. But the other one is connected to Q2. So now we figure out Q2. So Q2, we're going to draw it like this. This VGS2, we just flip it. And then here we have current source. And this is also grounded. And this is RO2. And this is a GM times VGS2. Okay. So VGS2, and now you see, okay, VGS1 and VGS2 are connected. Okay, so VGS1 and VGS2, so here, in the dotted line, they're connected. So I'm just going to connect them. And now you look at where is the drain of Q1 connected? Drain connected is connected to the source of Q3. So now we need to figure out the circuit for Q3. So Q3, we're going to draw the same thing. RO3. Okay, so they are connected. They're connected. Okay, I'm going to connect them. And this is where we're going to put our test voltage over here. And so this is GM3 times VGS3. Okay, so now where is the gate of Q3 connected? The gate of Q3, this is VGS. The gate of Q3 is connected to the drain of Q2. Okay, so because I need to, oops. The drain is connected to here. So the drain of Q2 is connected to the gate of Q3. Now, look at the circuit right now. It's basically finished. We finished the circuit. So in this circuit, one of the things that we can do is again for this one here, for Q1. So this one is GM times VGS1. If we convert that into a resistance, that's going to be VGS1. So VGS1 cancel, so R is equal to 1 over GM1. So this one can be connected to a resistance. So now if you simplify the circuit, this one becomes resistance. The Q1, the current over here becomes a resistance. I really don't like this way. I like to draw on a board, which makes it sense a lot easier, but I don't have the luxury. So this one can be replaced by this one. So you see, now you have two resistance in parallel. In the BJT case, you have resistance in parallel, but now you have only two, so a little easier. Here is the same. but the other one is not connected. You see, the circuit over here is basically like this circuit over here is standalone, right? It has nothing connected because the top one is open. The one we leave with the VGS, like a terminal over there, is only to calculate VGS3. So if we apply, in this case, if we it will be simpler if we apply a current called Ix, and let's calculate Vx. So if we input an Ix, what would you get over here? Same Ix, correct? See, if you get Ix, because there's no current here, so the current will flow from both and get here becomes Ix. And Ix, and this becomes two resistors in parallel. So I'm going to erase that one because you have it on the next page anyway. So I'm going to erase this to make it a resistor. And actually, I'm going to make this one resistor because that will make it simpler. So this resistor is R01 in parallel with 1 over GM1. So this Ix flowing down, you see the two ends just cables, there's no current. So everything goes down. So we get the voltage over here. Let's call it VD1. So how much is VD1? Oh, VD1 is VGS1 and VGS2 is the same. Did you see that? Okay. So I call this VD1. It's the same with VGS1, same with VGS2. It's all the same. So which is Ix times this. Okay. And now, and also, how much is the current over here? VGS2. So this gives you the current, and the current flowing this way, the current flowing this way. So really, you have voltage over here. We call VDS2. Okay, so VDS2 equal to minus, because look, the current is flowing up this way. So minus GM2 times VGS2 times RO2, okay? So you got this voltage, and VDS2 is equal to what? So VDS2 is here. And this voltage is equal to VGS3. So now you have the idea. So this one is really VGS3. So now you have no VGS3. How much voltage is between here and here? So let's call it VDS3. So VDS3 equal to current is Ix minus GM3 times VGS3. That's current. So Ix coming in minus current source gives you the current flowing through RO3. So this one times RO3 gives you VDS3. So your Vx, which is the voltage over here, so Vx is going to be VDS3 plus what we calculate VD1 first. Yeah, VD1. So you got Vx is equal to this. So finally, you can have RO equal to Vx over Ix. That will give you the output resistance. Yes, go ahead.
Like in previous example, there was an output resistance for the.
Our reference? Yeah, there would be one, yes. But here we don't consider it. We consider it an ideal current source. But if you look at this one, this is modified. Instead of using a current source, we add another one here. So this was further complicate the problem. But the idea here is that you can always draw the small signal equivalent circuit and then do the circuit analysis to find out what you can find for the resistance. So regardless it's 3, 4, 5, 6, 7, or 8, You can always use the small signal equivalent circuit. So today I use this example, really just want to get you to understand the procedures. Get the small signal equivalent circuit of the circuit and figure out what are connected to each terminal. Once you figure out what is connected to each terminal, then you can simplify the circuit and do the circuit analysis. So it really makes it simple if you can draw the small signal equivalent circuit. That's the most critical thing. So here, this is basically the circuit we draw from the last slide. And you can see here, everything is the same. Basically, they mark Vx. Yeah, so it's easier to use Ix to get all the voltage and then and so on. And you can calculate. So eventually, the resistance is derived. So I'm not gonna spend too much time on this. But as you can see, the resistance is much larger than just one current mirror. With one current mirror, you have the resistance RO2. So that's RO. But with this mirror, you have RO equal to this is GM times RO3 and times RO2. So this is like one stage. Remember in the last lecture that I gave on the recorded lecture, if you have this cascade amplifier, then you will further increase. So you can increase this one with multi-stage. You can have this one like equal to GM4 times RO4, and then times GM3 RO3 times RO2. Because you can have multiple stages. For every stage that you add, it increases resistance by the order of 1,000, something like that. So most of the time, we only need 2 stages because the resistance is already big enough, like in the mega ohm range, many mega ohm range. So we normally don't need many. Maybe one stage will increase the resistance from kilo ohm to mega ohm, and then the other one will increase to hundreds of mega ohm. So this is where this thing is so important. So now I'm going to use the next time to look at the common. Yeah. Any questions? Yeah.
So, all the concepts are exact.
They are identical.
So, the biggest change back.
Yeah, I reference can be changed. Yeah, to get the like here in this circuit. In this circuit, basically you can replace this one with the resistance instead of current source. So all the current will be depending on how much resistance you have. Yeah. Okay. So let's look at where is that? All right. Wilson. Where's Wilder? I forgot to copy the Wilder. Widlar. The Widlar. The Widlar current mirror is like this. If I remember correctly, you will have BJTs. So remember the current mirror that we have with BJTs, initially it's like this. It's like this. And with this current mirror, we have this current. If we assume like a battery infinity, make it easier, like a MOSFET. And then we have this IC equal to this IC, which is equal to IC equal to this VCC minus 0.7 divided by R reference. Okay. So this is how you get this regular current mirror. So suppose you want such amount of current, you will find out that this IC, this R, or you calculate R reference, is going to be VCC minus 0.7 divided by IC. So if IC is small, the reason that we want that current, like when we first learn this electronics, we always use milliamps. Which what happened in the early days, these devices were designed for milliamps. But when you have 1 million transistor, again, on a little chip, if each one conducts 1 milliamp, how many milliamps would you need? One million times 1 million. So 1 million is 10 to the 6, right? So 1 milliamp is 10 to the minus 3. So you have 10 to the 3 amps of current. For that kind of chip, you want to flow 1,000 amps of current? That's not feasible. It's not likely. But of course, they're not everything in parallel. Some of them are in series. But still, what I'm saying is that you need to reduce the current. So 1,000 amp is ridiculously high. So if we reduce that, let's say to 100 amps, then we would need to reduce the current from 1 milli to 100 micro. If you want to reduce the current from 1,000 to 10, we need to reduce the current from 1 milli to 10 micro. Okay. Then if we want to reduce to 1, you need to reduce to 1 micro. But there's a limit, because if it's too small, we just couldn't handle it because there's too much like a noise. It will couple and then things will make it more difficult. Yeah. So in this case, the current is small, typically in the microamps. When current is in microamps, and VCC, let's say it's 5 volts. Well, so 5 minus 0.7, 4.3. 4.3 divided by some current, you got hundreds of ohms, like 200, 400 something ohms. So that's very big resistor. When we design integrated circuits, it's very difficult to design resistance on a silicon. You know, silicon or semiconductor device, semiconductor is used to design semiconductor device. It's not to design a resistor. So it's very difficult to design a resistor. So it's for small resistor, it's a little easier, but for large resistor, it's difficult. So Widlar found this very interesting method that he does this. Well, instead, I'm going to do this. So you might already look at the circuit. Well, the only difference between these two is RE over here. But adding that RE makes a huge difference in the current mirror because it's no longer a current mirror. Because if you look at the circuit like right now, these two are not going to have the same current. It's not going to have some current. Why? Well, how do you calculate the current in a BJT? Remember, a current in a BJT is like this. If you guys remember, IC is equal to IS times e to the power VP over VT, correct? Is this expression correct? Hopefully it's correct. So IS can be the same for both resistors, both the transistors, but VPE in this case is not the same. But in this case, like in this example, VPE1 and VPE2 are the same. But in this case, are not the same. Why not the same? Well, we don't know really, but they're probably not going to be the same because there's a resistor over here. And that is connected directly to ground. So in this case, we can calculate IC1 and IC2. Okay, so we calculate IC1. So we calculate IC1, we simply become this one, VBE2 and V2. So that's how we would write IC1 and IC2 in the two circuits. And then but if you look at VBE1 and VBE2, what is the relation between, well, assume B is beta is infinity now. So IC2 will be same as IE2. Okay. And assume this one happens. What's the relation between VBE1 and VBE2? Can you tell me that? So VBE1 equal to VBE2 plus IE2 times RE. Did you get that? Right. So in that sense, we have IE2 equal to VBE1 minus VBE2 divided by all, in the sense that we're gonna just we're gonna get RE equal to this one divided by RE2. And you plug in if you plug in this RE2 is IC2, which is here. Okay. And what you can do is you can get so for the top equations, VBE1, you can express VBE1 as a function of IC1. You can express VBE2 as a function of IC2. Okay, and this is IC2, and you plug everything, you will be able to find the exact expression of current for this case. And I don't remember the expression. That's how you calculate. So anybody has a book? Nobody carries their sick book anymore, right? So let me do this. Let me see if I have. Let's see. Okay, so here is. Okay, so here is. So this is the expression. So I moved too early. Basically, this is why this is so small. But the calculation of RE is basically what we derived over here. Yeah. So this is what we have derived this equation over this equation. So now we have this well, Widlar and also So what I'm gonna do is, we still have another 15 minutes. So I'm gonna go to the concept about how to draw this equivalent circuit for this common gate and a common base amplifier. We're not gonna go to the detailed equations anymore because we don't have the time. But again, I want to illustrate how you can do step by step by looking at the using the equivalent circuit. So for the common gate, let's do a common gate first. My pen doesn't write anymore. Something else crazy. Let me see if I can write it here. Write it here. Okay, I can write here. So the comma, let's do this comma. When you say comma gate, we know that the gate is grounded. So, and then if we have this, for now, we can use resistance as a load over here. So this is VDD. And we're gonna have an input connected to that's how it looks like for a common gate amplifier. So for this common gate amplifier, if we want to get, like, for example, what is the output for small signal? And what is the input resistance? What is the output resistance? So way to get it, the only way to get it is to draw the small signal equivalent circuit. So over here, we can draw the small signal equivalent circuit by start drawing the MOSFET. Okay. So now, once we draw this, the MOSFET, now you figure out the gate, the gate, the drain, and the source. So if you look at the gate is connected to ground. Okay, so this is your VGS, and your drain is connected to what? Well, which this is your VO, but you see your drain is also connected to RD. Then RD is connected to VDD, and VDD is the ground for AC. Okay, so so that's done. So drains is done, and gate is done. And now we look at the source. What is connected to the source? Basically, the source, you have a current source, which is input. In the book, I think called SIG. Then you have RE. So that's your source. Your source has two things connected. So if you look at this circuit, it's not that difficult because you only have really just like one node over here. Like this one is a huge node. So in the sense that you can also draw like a equivalent circuit by this. There's one thing I want to make sure you understand, that RO and RD are not in parallel in this case. Because in some, like in common source amplifier, these two are in parallel because they're both grounded. But in this case, RO is not grounded. So RO is connected to the source. So it's not in parallel with RD. Okay, so that's important. So once you figure out that, you can you can do many things. Like for example, if you want to find out what the input resistance is, you can apply a current at the input over here. Oops, wrong plane. And you can apply current over here, and you calculate the voltage, and then you can calculate basically that. And if we want to calculate, for example, the output resistance, what we can do is we can redraw the circuit like this. Now, when we look at the output resistance, we neglect RD because that's the load. And here we have, okay. We have RS and RO. This is GM, VGS. And VGS is grounded over here. You see, in this case, let's separate them. So in this case, if we look at here, the voltage over here, let's call it VE. So this VE will be IX times RS. And this equal to minus VGS. From here to here, the VGS. But from here to here is VE. So plus minus, that's VE. Okay. So so you have VE. Now you also need to calculate this this voltage over here. So from here to here, that's called V1. So that V1 equal to IX minus GM times VGS, and then times RO. Yeah, times RO. So that's V1. And then your Vx equal to V1 plus VE. So your RO is Vx over Ix. Of course, you have to do some mathematical manipulation in order to derive the relation between Vx and Ix. But eventually they will cancel, so you get purely resistance. So this is the common gate amplifier. If we want to do why? So I cannot, it doesn't go to, okay, I cannot change to any. Oh, a lot of stuff on the screen. How do we erase this thing? I'll probably can just erase everything. Oh, this all messed up. Yeah, I guess I have to just erase them. But all this diagrams and equations, everything is in the book. So you don't have to copy this because it's in the book, and also it will be in the slides that that we are going to. I'm not sure why. Really weird. Something's wrong. Okay, so probably let me, if I something wrong with my pen. Then it's wrong. Oops. It just come up. Oh. Maybe I'll do this. Okay, so this is yeah, so this is the common gate, but we draw that already. And this is the process how to derive the resistance, blah blah blah. And it's in particularly what's important is that the resistance okay. So what we can do is let's draw this common. We're gonna get this one, then we'll be done. So this one is your VCC, this RC. This is the common base. And with common base, apparently okay. So this is exactly the same as the previous circuit, but only that this here is the BJT. With the BJT, the complexity comes to this R pi. So if you draw the circuit, that's the equivalent circuit. This is R pi, this is RO, and this is GM times V pi. The V pi is here, the V pi. So the gates, I mean the drain is connected to RC, which is going to ground, and this is your VO. And now we need to figure out what is connected to the gate, I mean to the base, which is ground. So that's why this is called a common base amplifier. And what is connected to the emitter then? What the emitter connected to is a resistor RE. So you have this. So now for this circuit, the only difference you see here is where you have this R pi. So this R pi here will complicate the whole like calculation process. It makes the process like you have to be really careful to derive the actual input resistance, output resistance, and gain. But as I mentioned from my previous lectures, in this class, I'm not looking at too much about the actual final like answer. I'm looking about the process that how you draw the equivalent circuit. So if you guys go back to make sure you can draw the equivalent circuit for any given circuit. So you probably want to look at the book. There's a bunch of homework problems in each chapter. Just try to draw their equivalent circuit. You know, anyone, regardless how the external circuit is connected, you can draw the equivalent circuit. That's the most important thing. Okay, so exact 6:15. Thank you. We'll see you Wednesday. Remember, we have a quiz. Yeah. Yeah. I should have called it RS. This is RE for the freeway for anything. Yeah. Yeah. Well, what's the source is the ground for AC. When you do superposition, it's usually becoming closer. We're pretty much doing the superposition now.
Right now? Allow me. Yeah, all right. Catch that. I'm gonna. Yeah. So like you're
Bye.
now here. Yeah. We're out. Yeah. I don't know. I don't know if